back to my YouTube channel all about VLSI. Welcome to Verilog Project Development Series, where we are developing few projects related to Verilog. And in this process, we have developed the carry save adder, and we've also developed the SRAM controller. And in this particular session, we are going to try to develop Sobel Edge Detector. Now, before going to discuss about Sobel Edge Detector, we need to know some prerequisites. So, for that, I'm planning this particular session, right? Now, first of all, we need to understand what do you mean by a color image and what do you mean by a gray image, right? So basically, gray image or a grayscale image, it is only going to have two components. One is brightness information, and it is not going to have no color information, right? So each pixel represents how dark or bright that particular location is. Whether that particular location is very dark or whether that particular location is very bright. Using the grayscale images, you cannot represent a color image, right? So, for example, if the pixel value is 0, then it is dark black, and if the pixel value is 255, then it is white. And let's say if the pixel value is 128, it's a gray image, right? And so, very lower the value, it is darker, and very higher the value, it is brighter, right? Now, why are these gray images are used? So basically these are used because they are going to consume less memory compared to your color images. Your gray images is going to consume less memory, and these are easier to process because these are only going to have two fields. These are basically represented in rows and columns. I will show you how we are going to represent it. And these are very faster algorithms, and it is also used in edge detection. Where if we are going to perform edge detection, like here in our project Sobel Edge Detection, we are going to use gray images only. And for medical imaging, OCR, computer vision processing, we are going to use this gray images. Now, whereas in the case of my color image, it is going to contain brightness as well as color information also. Whereas in the case of my gray images, I cannot basically represent my color, but in the case of my color image, I can also represent my color information and also brightness. So the most common format is RGB image, where R stands for red, G stands for green, and blue stands for blue. Now, every pixel, it is going to tell us amount of red, amount of green, and amount of blue. In the case of my grayscale images, if I'm going to have a pixel is nothing but it's a picture element. See, if we are going to have an image like this, digitally, this particular image is made up of small picture elements, which is known as pixel. In the case of my grayscale image, this pixel will be either black or it will be full white or in between black and white, which is shades of gray, right? This is nothing but my grayscale image. And this picture is made up of this small picture elements. But in the case of my color image, let's say if I'm going to have a color image like this, each pixel is again going to have subpixels. So this image is made up of a pixel, and this pixel is again made up of three subpixels like this. So which one subpixel represents red, and another subpixel represents green, and one more, the last subpixel represents blue. So each pixel is made up of this subpixels like this, and combination of this red, green, and blue in some amounts gives us different colors. We will see about that particular thing in upcoming slides. Yeah, this is what I was talking about. Let's say if I have a pixel, in this particular pixel, if I'm going to have pure red and green subpixel information is 0 and the blue subpixel information is equal to 0, then it's a pure red color. So this particular pixel corresponds to red, right? So this subpixel value, if it is equal to 255 and green subpixel value is equal to 0 and blue subpixel value, if it is equal to 0, then it is a pure red. Now, so let's say if every subpixel information is equal to 255, 255, 255, then it is equal to pure white. Okay. If we want golden yellow, then red subpixel value should be equal to 255 and blue subpixel value equal to 223 and green subpixel value should be equal to 0. So like this, depending upon which color do we want, we are going to decide what should be the intensity of red, blue and green. Now, we calculate RGB values based on additive color mixing and digital intensity scales. I use it to personally, I use it to have this particular doubt, like how we are going to decide the red, blue, green values. Like if I want to have light yellow color, then how I'm going to decide the red intensity value, how I'm going to decide the blue intensity value and green intensity value. So this was my personal query. So the reason for this is there is something known as additive color modeling. So basically, screen uses lights for creating the color, and when the screen has tiny pixels made up of three subpixels, as I've told you, which is nothing but red, green, and blue. Now, mixing this particular lights in different mixing light is different than mixing paint. So if you're going to mix paint, then you know that we are going to get different colors, and that is entirely different from mixing this particular light. So don't get confused with this particular with this or don't relate this with mixing with paint, right? And when we are going to mix red light and green light, our eyes are going to perceive it as yellow. So this is how we are going to decide what should be the intensity of red pixel and what should be the intensity of green pixel, so that what color our eye is going to perceive. Okay. And there is something known as color theory, where we are going to mix some kind of colors to get one kind of color. No, that is entirely different, right? So this is one method. And second method is 8-bit digital scale. So computers store color data in 8-bit chunks for each channel, and this allows a range from 0 to 255 for each color. So total 256 steps, where 0 means completely turned off, which is black, and 255 means 100%, which is nothing but full brightness white. So in between, let's say if 0, there is no light which is present, and uh, 255 means high white light. And in between, we are going to decide what should be the intensity of red light, what should be the intensity of green light, and what should be the intensity of blue light. And mixing these three kind of lights, our eye is going to pursue a particular color. So this is how we are going to generate a color image. And yeah, and how we are going to store the images. So in the case of my grayscale images, these are stored in height and width. So I'm going to store the pixels, like for example 5, I mean 255, 0, 200, 5, 244. Like this I'm going to have it, and 220. So like this I'm going to store my grayscale images in rows and columns, height into width. In the case of my RGB image, I'm going to have R plane, green plane, and blue plane. So like this, I'm going to represent the RGB images in three channels. This is R plane, and this is G plane, and this is blue plane. Where a color image is not a one matrix, it is basically three matrices: red, green, and blue. This is what I was saying about, right? Now, as I was saying you earlier, that pixel is nothing but it's a picture element, and it is the smallest unit of a digital image. And the software view of the pixel, if you want to know it, so basically this particular software view of this particular pixel, it is nothing but it's a numerical value. So it may be 255 from 0 to 255. 0 is nothing but completely black, and 255 is nothing but completely white. And between the 0 to 255, we are going to decide. In the case of my grayscale images, it is shades of gray. In the case of my color image, it is nothing but the intensity of red, intensity of green, and intensity of blue. Now, so physically on a display, pixel is actually a tiny light element on a screen, where each display pixel contains red subpixel, green subpixel, and blue subpixel. So when we see from far, human eye mixes R plus G plus B, and it is going to pursue one color. This is what I was saying about, right? For example, if I'm going to have a resolution, like we might have seen this kind of resolution, like 1920 rows, I mean 1920 columns, and 1080 rows. That means basically I'm going to have 2 million pixels. I'm going to, if I multiply it, I'm going to have this many numbers. And if I'm going to have only one bit, I'm going to have two levels. And if I'm going to have two bits, I'm going to have four levels, and so on. Like if I'm going to have 8 bits, I'm going to have 256 levels. So this is 256 level in intensities. So I have 256 intensities, right? And why especially this 256, and why each pixel is represented using 8 bits? Let us try to understand over here. So the main reason is our human eye. So human vision cannot easily distinguish between very tiny brightness differences. Let's say suppose if the red color is having different red colors are having very tiny brightness differences, our eye cannot distinguish it. So that's the reason 256 levels it appears very smooth to most of the people. So that's the reason we are confined to only 8 bits. So that means we are going to have 2 power 8, that is 256 levels, right? Yeah. So that was about the prerequisites that we want to have the project, or that we want to do the project of edge detection, which is Sobel edge detection. And in our next session, we are going to discuss about what is edge detection and what do you mean by Sobel edge detection, what is mean by gradient and what do you mean by row gradient and horizontal gradient and all, and what do you mean by edge, how we are going to follow it. And after that, discussing that, we are going to see how to develop a Verilog code for edge detection on an image, right? So that's about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.